Welcome to AI Paper Slop, where we summarize the latest machine learning and tech papers so you can stay ahead of the curve. Today, we are skipping the fluff and jumping straight into a massive claim out of Ex-Humanoid.
Oh yeah, this one is huge.
Right. So the paper is called Pelican-Unified 1.0, a unified embodied intelligence model for understanding, reasoning, imagination, and action.
Quite a mouthful, but the core insight is exactly what we've been waiting for.
Exactly. So here's the TLDR for you. The authors argue that foundation models for embodied AI just shouldn't be built as these fragmented pipelines anymore.
Right, like wiring a separate vision model, a language model, a world model, and an action policy altogether.
Yeah, abandoning that completely. Instead, Pelican-Unified 1.0 integrates understanding, reasoning, imagination, and action into a single adaptive intelligence loop.
Which is wild.
It uses a single vision language model to generate a chain of thought and a dense latent variable. And then that variable is fed into a unified diffusion transformer that simultaneously denoises future video, which is essentially its imagination and the continuous robot actions.
And they do this with a single checkpoint.
Yes, a single checkpoint achieving state-of-the-art across VLM reasoning, world modeling, and physical visuomotor tasks.
It fundamentally challenges the assumption that you need isolated experts to handle different modalities in robotics.
Right.
Achieving SOTA across all three of those domains with one architecture is basically the holy grail of physical intelligence. We're moving from just modular accumulation to true structural unification.
So to really understand why Pelican-Unified is such a leap, we need to look at the architectural ceilings that current models are hitting. Because if you look at the current landscape of embodied AI, it is highly fragmented.
Oh, completely.
You have vision language models, things like Gemini Robotics ER or Pelican VL, and they possess incredibly strong semantic understanding, right? Like spatial temporal reasoning.
Yeah, they can parse a complex scene, identify object affordances, tell exactly what is happening spatially, but they're fundamentally passive observers. They aren't executable physical policies.
Right, they can't do anything.
Exactly. They can output a perfectly reasoned text description of how to move a box, but they can't actually actuate a robotic arm or test that reasoning or ground their conclusions in the outcomes of their own physical behavior.
Right. Then you have the vision language action models, the VLAs like RT2 or Pi0, which try to bridge that gap.
And those take that language and perception and map it directly to motor commands.
Right. But if you've ever actually deployed a VLA, you know they lack explicit future imagination.
Yes. That's the big flaw.
Because they don't explicitly simulate what the future state of the world should look like after they move, their actions usually just devolve into these simple imitation mappings.
Which is exactly why they severely struggle with generalization to unseen compositions or, contact-rich interactions. Long horizon tasks are just a nightmare for them.
Yeah, because when a VLA makes even a slight kinematic error, it doesn't have an internal visual representation of what should be happening to correct itself.
Exactly. It just keeps mapping the current flawed state to the next action based on its training distribution.
Which is just a compounding disaster. And then on the other end of the spectrum, we have the pure world models, like Cosmos Predict.
Right, sitting there generating stunning future pixels.
Yeah. They can imagine a highly realistic video of a robotic interaction, but because they are trained primarily on pixel reconstruction, they are incredibly hard to steer with language-grounded task logic.
It's like the system is just broken into silos. The semantic models can't move. The action models can't imagine, and the imagination models can't reason.
It's like a highly compartmentalized corporate bureaucracy. You've got the vision department sending an email to the action department, but they don't actually share a brain.
That's a perfect analogy.
So it leads to these massive communication breakdowns during complex tasks.
And the paper's central thesis is that the missing capability in each of these specialists is not just an optional add-on.
Right.
It's the fundamental ceiling limiting their performance.
Yeah.
A policy without future imagination remains weakly consequence-aware. A world model without unified reasoning remains really difficult to steer. And reasoning without action remains totally detached from physical outcomes.
Okay, but look, whenever a paper slaps the word unified on their architecture, my immediate assumption is that they are just doing some form of clever concatenation.
Of course. That's what everyone died.
Right. It's incredibly common to see separate expert networks wired into a sequential pipeline or a mixture of experts setup masquerading as a unified system.
Yeah, just sticking them together.
But if Pelican-Unified is claiming a single checkpoint beats the specialists, they can't just be passing text outputs from a frozen VLM into a separate diffusion model.
Right, and they aren't. The authors are very strict about their definition of unification here.
Okay.
They do not mean simple concatenation or pipelining. They mean structurally shared representations, mutually constrained conditions, and coevolution through a common training process.
So they are actually training together.
Yes. The text, the video, and the action losses all backpropagate through the exact same shared representation. It's a true end-to-end objective.
Wow.
Language, video, and action supervision are trained jointly, which means gradients from a physical motor error actively update the weights governing semantic understanding.
That is wild. Okay, let's break down how that loop is actually built, starting with how the model understands and reasons before it actuates anything.
Sure.
So they initialize the system with a single VLM backbone, specifically Qwen3 VLL4B.
Right, and the input to this VLM is a multimodal context window. It takes in the observation history, so the sequence of previous frames.
Okay.
It takes the previous actions the robot has taken and the natural language instruction. And from that context, it produces a chain of thought reasoning trace.
Now wait. We see CoT all the time in large language models solving math problems, but a text-based monologue doesn't inherently know how to drive a 6-degree of freedom robotic arm.
It doesn't.
The text decoder is generating tokens. How does a sequence of linguistic tokens translate into an executable physical policy without just relying on a brittle text-to-action mapping?
And this is where the architecture makes a really critical departure from standard VLMs.
Okay.
The reasoning trace isn't just a detached explanation. The hidden state of the VLM, captured right after it constructs that chain of thought, but before it outputs raw text, is projected into a dense loop state.
Okay, I see.
The authors refer to this as the latent variable Z.
Got it. And if the downstream loss is a flow matching objective for both video and actions, and those losses are backpropagating all the way up through the network, then that latent variable Z is being heavily pressured by the physics of the world.
Exactly.
It's no longer just encoding language semantics.
That is the crucial mechanism right there. Because Z serves as the universal interface for the downstream generative process, the network is forced to encode highly predictive physical information into that dense vector. To minimize the video reconstruction loss and the action trajectory loss simultaneously, Z basically has to become a compressed physical simulator.
Oh, wow.
Yeah, it represents the holistic understanding of what the agent sees, what it intends to do, the physical constraints of the environment, and the historical state of the world.
Okay, so we have this incredibly rich, latent bottleneck, Z, holding all this physical and semantic intent.
Yes.
Now we have to translate that into simultaneously imagining the future and executing a movement. This brings us to the Unified Future Generator, or UFG, which they initialize from 1.2.25b, which is a diffusion transformer.
Right. And in a traditional setup, you would split this into an independent world model for video prediction and a separate policy head for action generation.
Because they're totally different things.
Exactly. But Pelican-Unified abandons that. Both the video latent and the continuous action trajectory are embedded into the exact same transformer width.
Okay, but if you've ever tried to train a diffusion model, you'll spot the immediate problem here.
Yeah.
You are taking video, which exists in a spatial pixel-based domain.
Right.
And you are taking action, which exists in a kinematic trajectory space. We're talking joint angles, torques, gripper states.
Completely different distributions.
Embedding both into the same attention blocks sounds like a recipe for absolute numerical collapse. How do spatial tokens and kinematic tokens not entirely destroy each other during the denoising process?
Well, it seems like they should, right? But they align them mathematically through a continuous time flow matching objective.
Okay, how does that work?
Without abstracting away the math too much, what happens is both the video and the action modalities share the exact same diffusion time S.
Interesting.
The modalities are projected into a shared dimensional space and denoised by the exact same transformer backbone.
So they're adding noise to both the future video latents and the future action chunks simultaneously, and asking the transformer to denoise them as a joint distribution.
Yes. And during that denoising process, the self-attention mechanism models the temporal and spatial dependencies across both modalities.
So they are talking to each other.
Literally. The video tokens and the action tokens are attending to each other. Meanwhile, the shared task state, our dense latent variable Z from the VLM, is injected into the process via cross-attention.
Think about what this actually means for the robot's internal representation.
Yeah.
The predicted physical movement actively alters the imagined video frame, and the imagined physics of the video frame actively correct the kinematic trajectory.
Exactly. If the action tokens predict the arm moving left, they attend to the video tokens to ensure the imagined pixels physically reflect that leftward movement.
That's brilliant.
And it works in reverse as well. If the video tokens are imagining a dense, heavy object that doesn't displace easily based on the physical priors learned during pre-training, that spatial information informs the action tokens to adjust the trajectory.
Like applying more simulated force.
Precisely. Modality-specific parameters are isolated only to the input and output conversion layers.
So the core is completely shared.
The core denoising computation is entirely shared, meaning actions are continually shaped by imagined consequences, and imagination is rigidly framed by executable task reasoning.
That is so cool. But look, theoretically, elegant architectures often collapse when you actually try to run them across diverse benchmarks.
Oh, for sure. The jack-of-all-trades problem.
Right. The assumption in machine learning is always that forcing a network to do everything results in a compromise in performance. If you force a model to imagine high-fidelity video, doesn't it degrade its ability to simply move a robot arm effectively?
You would think so, but the paper addresses this directly through what we can think of as a triathlete test.
Okay.
They evaluated Pelican-Unified 1.0 in 3 deliberately separated regimes, basically grading it as if it were 3 distinct specialist models. The empirical results show that unification in this specific architecture does not imply compromise. A single checkpoint matches or beats dedicated specialists across every single domain tested.
That's insane. So for VLM understanding, they ran it across 8 different benchmarks, achieving an average score of 64.7.
Which is state-of-the-art for comparable scale models.
Yeah, but what's really telling is how it compares to prior VLA architectures. A model like Mulmoax scored a 27.5 on these same benchmarks.
That's a massive gap.
Why the huge difference? Because typically, when you fine-tune a VLA on motor tasks, you either have to freeze the vision backbone, limiting its adaptability, or you get catastrophic forgetting that ruins its semantic understanding.
Right, and Pelican-Unified avoids that entirely because of the joint training objective. The semantic understanding actually improves because it gains spatial and physical grounding.
Oh, that makes sense.
You see this explicitly in embody-oriented benchmarks like where to place NFX, where the model massively outperforms baselines because its understanding of the image is tethered to its understanding of how objects move and interact physically.
Okay, and for purely action-based capabilities, they tested it on RoboTwin, a dual-arm simulator benchmark, where it achieved a 93.5% average success rate.
Yeah, that places it second overall among all compared dedicated action methods. So it's a highly competitive visual motor policy on its own.
But the most revealing benchmark has to be its performance as a world model, right? Evaluating its imagination capability.
Absolutely. On the World Arena benchmark, it ranked first with a score of 66.03, outright beating dedicated world models.
And we really need to look closely at the human evaluation metrics they ran for World Arena.
Yeah, this part is fascinating.
Human evaluators graded the generated videos on a scale from 0 to 2. Pelican-Unified received a perfect 2.00 on controllability and a 1.81 on task success.
Which is huge when you compare it to the alternative.
Exactly. If you look at pure video diffusion models, models built exclusively to generate video like SOTA or Kling, they often score near 0 on task success in these robotic benchmarks.
Right, because they just hallucinate.
Yeah, they generate visually stunning, temporally smooth videos that entirely abandon the requested task. The pixels look gorgeous, but the robot arm might clip right through a solid table.
Because pure video generators optimize heavily for pixel-level fidelity and temporal smoothness, but they have 0 underlying representation of manipulability or physical constraints.
Right.
Pelican-Unified is pre-trained on large-scale, real-world robot interaction data. It learns 3D geometry cues like depth, object permanence, and viewpoint consistency naturally from the physical data distribution, rather than relying on some explicit physics engine.
Because its generation process is conditioned by that latent Z, and it's forced to output actionable kinematic tokens alongside the video, it is physically incapable of just daydreaming a pretty video.
Exactly. It has to dream a video that the action tokens can actually execute. The imagination is constrained by the reality of the robot's physical embodiment.
And the competitive motion quality scores confirm this. The model doesn't just generate plausible visual scenes, it generates temporally coherent motions that strictly adhere to actual kinematic limits and environmental dynamics.
Right.
But simulation benchmarks are great for papers, right? Physical hardware is where these models usually fall apart.
Oh, hardware is famously unforgiving.
The real world doesn't care about a flow matching objective. If the robotic arm drops a glass of water due to a minor calibration error. So how does this closed loop system operate when deployed on actual hardware?
Well, they deployed the model on a real UR5E robotic arm and a King Kong humanoid robot operating in environments like industrial control panels.
Okay.
The most critical experiment they ran on this hardware was a compositional generalization test designed specifically to break traditional VLAs.
All right, set this up for us.
Okay, so during training, the model is trained independently on task A and task B. Let's say task A is plugging in an RJ45 connector and task B is inserting a waterproof connector.
Okay, two distinct tasks.
The model learns these separately. Crucially, it has never shown a combined demonstration of task A followed immediately by task B.
Got it. So there's zero training data containing the complete chain sequence of those two actions.
Exactly. Zero.
So during inference on the physical robot, they give it a single natural language instruction requiring it to execute both sequentially.
Right.
Think of this like compiling software code for a minute. You can successfully compile module A, and you can successfully compile module B independently.
Sure.
But if you try to execute them sequentially, and module B requires a highly specific memory state that module A outputs, but the system doesn't know how to pass those pointers, you get a segmentation fault. The program just crashes.
That is an excellent way to conceptualize the failure mode of traditional VLAs. They experience a robotic segmentation fault at the transition point.
Right.
It isn't a failure of perception. They can re-perceive the environment after task A.
Yeah.
The failure is that their action distributions carry no internal representation of the transition state. They don't know what the physical environment is supposed to look like or feel like when task A is completed in preparation for task B.
It's like learning to bake a cake and learning to frost a cake in completely different classes, but never practicing them together.
Yes.
If you don't know what a hot, freshly baked cake looks like, you'll melt the frosting. So how does Pelican-Unified avoid this transition state failure when it has literally never seen the combined sequence?
It leverages its unified imagination phase.
Okay, how?
As the robot physically completes task A, the model uses its diffusion transformer to render the post-task A scene visually in its latent space.
Wow.
It imagines the physical state of the world with the RJ45 cable successfully plugged in.
Incredible.
Then it reconditions its internal loop state, our latent Z, based on that imagined physical reality, seamlessly populating the required parameters to proceed to the action phase for task B.
Wait, so it literally visualizes the end state of the first task to synthesize the starting conditions for the second task, all within its internal representations before it ever moves the motors for the second task.
Yes. The fact that it executes this perfectly on physical hardware without chained training data is profound evidence that it has internalized the perception-action loop, rather than just memorizing a dense action policy.
That's a huge distinction.
The authors even compared the real execution videos from the hardware rollout with the corresponding imagination videos generated by the model during the task, and the physical dynamics match the imagined dynamics incredibly closely.
So it isn't hallucinating at all.
No, it is successfully predicting real-world environment dynamics.
Which brings us to the broader implications of this research. Because what the authors are presenting here is a fundamental paradigm shift for embodied AI.
A total shift.
The path forward is no longer about scaling up isolated specialist models. We aren't going to solve robotics by just building a larger vision language model, training a massive separate action policy, and hoping they communicate effectively through an API.
Now, that era is ending. We have to scale the shared unified loop itself.
Right.
We need architectures that force semantic understanding, physical reasoning, visual imagination, and kinematic action to co-evolve through a shared representation.
Because the relevant unit of scaling is the closed loop.
Exactly. As the authors emphasize, the capabilities of a system are bottlenecked by its most isolated component. You cannot achieve true physical intelligence if the reasoning engine doesn't feel the gradients of physical failure, or if the action policy can't explicitly simulate the future consequences of its movements.
Right.
By unifying these modalities into a single, continuous time flow matching objective, Pelican-Unified demonstrates that mutual constraint creates a far more robust physical agent.
It's an incredibly compelling architecture backed by aggressive empirical results. But, it does leave us with a really significant question regarding the future of the field.
You have the data problem.
Exactly. The paper proves that a unified training objective creates a superior physical intelligence. However, as noted in their methodology, this architecture requires highly specific, strictly aligned data.
Very specific data.
You need training examples where the observation history, the language instruction, the reasoning trace, the physical action trajectory, and the future visual outcome are all perfectly aligned on the exact same robotic interaction.
Which is incredibly hard to get.
That data does not exist in typical internet datasets.
It highlights a massive bottleneck. The traditional approach of scraping the web for text and video to train foundation models is largely useless for this specific unified objective.
Exactly. You can't just scrape YouTube for this. So here's a final thought to leave you with.
Go for it.
As we hit the limits of what traditional internet scraping can teach a physical system, because there simply aren't billions of aligned videos of robots reasoning through industrial tasks while logging their drained torques, will the next trillion-dollar AI moat simply be who can build and operate the most massive closed-loop physical robot data farms to feed these unified architectures?
That's a great question.
Because if unification is the ceiling, the data to train it might just be the most valuable resource in the next decade of AI development.
I wouldn't bet against it.
Thanks for joining us for this deep dive into Pelican-Unified. Catch you on the next episode of AI Paper Slop.